In an earlier lesson, we developed the concept of a confidence interval for one proportion. So the logic in constructing and interpreting these two sample intervals is the same as the one sample interval. The only major difference is the standard deviation. We will develop the formula for the two sample proportion interval. However, don't get too concerned with all the mechanics. You should use your calculator to prop z interval or StatCrunch to do these computations. The textbook readings have more details on the derivation of the sampling distributions for the difference between two independent proportions. Let's start with the type of problem you'd be expected to do, and we'll develop the concepts within the first example, and then the examples that follow will rely primarily on technology to carry out the computation. Example 1. Suppose that the superintendent takes a random sample of 90 students from the over 1,000 students taking the AP Statistics from all the AP Statistics classes and finds that 76% of the 50 females were satisfied with the class, while 50% of the 40 males were satisfied with the class. Construct a 95% confidence interval to estimate the difference in satisfaction rates between the males and females. So step 1, we want to verify conditions just to make sure there are no red flags. So just like the one sample proportion, we have similar conditions. Simple random sample, it says you took a simple random sample, so that one's verified. 10% condition, sample size of 90 is less than 10% of 1,000. Independent groups, the two groups should be independent of each other, and they are, we're assuming. So the sample size needs to be big enough. So we check both sample proportions. So N1, P1 bigger than 10, N1 times 1 minus P1 is greater than 10. And same thing for sample 2. And we check these. 50 times 0.76 is greater than 10. 50 times 1 minus 0.76 is bigger than 10. And then the next one, 40 times 0.5 is bigger than 10. And 40 times 1 minus 0.5 is certainly bigger than 10. So let's start with the general notion we did in the earlier lesson. Point estimate plus or minus margin of error. As you recall, the margin of error is made up of two parts, the critical value and the standard error. With the one sample proportion, we have p hat plus or minus the critical value times standard error. So p hat plus or minus the critical value times the square root of p hat times 1 minus p hat all over n. This should look familiar. If not, please go back and look at that lesson on one sample proportion intervals. So with two samples, we're finding the difference. In our example, we're comparing the 76% of the females who were satisfied with the course with the 50% of the males. So obviously our difference between the two sample proportions is 0.76 minus 0.5, or 26%, 0.26. However, this is just our particular simple random sample. How can we estimate the true difference of the entire population of statistics students, females versus males? So again, similar to the one sample, if we could just have one number to point to, this would be it, 26% difference. However, as before, it's better to give an interval of plausible values. So a different sample would lead to a slightly different result. And so because while 26% seems like a large margin, is this difference due to just random sampling? Let's go ahead and add and subtract the margin of error. Let's start with the standard error term for p hat sub 1 and p hat sub 2. So recall, I can't subtract standard deviations. However, I can subtract the variances. That is, the variance of the difference is the sum of the variances. So go back and look in an earlier module if you've forgotten that, and the reason why we add the variances, so long as our samples are independent. And so substituting our standard deviations in to compute variances, we have the variance of the first one squared plus the variance of the second one squared. And the square just undoes the square root, right? Leaving us with p1 times 1 minus p1 over n1 plus p2 times 1 minus p2 over n2. Now take the square root of both sides, because ultimately we need the standard deviation, right? Which gives us standard deviation of the difference is the square root of p1 times 1 minus p1 over n1 plus p2 times 1 minus p2 over n2. Well, because we don't know the population parameters p1 and p2, as before, we're going to use our sample statistics. P hat 1 and P hat 2, we'll call them. And this gives us the standard error as follows. So the SE for standard error of the difference, square root of P hat sub 1 times 1 minus P hat sub 1 over N1 plus P hat sub 2 times 1 minus P hat sub 2 over N2 in the square root. So recall that we subtracted our two sample proportions We just found the standard error of our estimate. Let's plug that into our our pattern. We put in our critical value, z star or z sub alpha over 2. If we're looking for 95% confidence interval, z would be 1.96 as usual. So we will use this formula in the first example, and after that, we're just going to stick with technology. The computations can get kind of tedious by hand. So back to our example. So we've already verified the assumptions. Now let's plug into the formula. It can get a little confusing if you use subscripts 1 and 2, at least for me it does. So either define which sample is 1, let 1 be the females, let 2 be the males, or even better, sometimes is to make the subscripts actually sort of remind you what the samples are. So rather than using the subscripts 1 and 2, I'm going to use F and M for female and male. And we'll often also use parentheses around the difference of the two proportions, just for aesthetics. It looks a little better that way. So now I don't have to think quite as much. I can plug in directly. I already have 0.76 and 0.5. I just plug all those straight in. Make sure you get the number correct. Number of females is 50, number of males is 40. And now we just compute as before. We simplify into the radical. It leaves me with, I have 0.26 plus or minus 1.96 times 0.09949, which is the standard error term, right? That 0.09949. Multiply the standard error by the 1.96 to get my margin of error. So I'm going to have 0.26 plus or minus 0.195. Now it's in my form of point estimate plus or minus the margin of error. Sometimes we can just stop here. If it's a multiple choice and they've given them all this way, you can leave them that way. But let's write it as an interval by adding and subtracting that margin of error to and from 0.26. And we'll get 0.065 and 0.455 in parentheses. Now let's interpret this interval. These can get a little confusing with two samples. So we are 95% confident that the true difference between the two population proportions is between 6.5% and 45.5%. So technically that's okay. Let's see if we can reword this a little bit to where it sounds a little more natural. So also let's put it in context. We are 95% confident that the proportion of females who are satisfied with the course is between 6.5% and 45.5% more than the proportion of males who are satisfied with the course. A rather large interval. So what can we do if we were asked to make that margin of error less than, it's close to 20%, right? 19.5% margin of error. Good, I need to increase my sample size, or I could lower my level of confidence. Now we're going to use technology to do the computation. So on the TI-84, press Stat, scroll to Test, and select 2prop_z interval. Next, input your x1, n1, x2, n2. Now for our problem, I had to multiply 0.76 times 50 to find out what x was, and similar with x2. So you will see the interval displayed along with p hat 1, p hat 2, n1, and n2. So note this is exactly the same interval that we obtained by hand. So of course the interpretation is going to be the same. Now in StatCrunch, we get the same thing. Again, go to StatCrunch, go to Stat, Proportion Stats, to Sample with Summary. Put in the values for the number of successes and observations, as shown here, 38, 50, 20, and 40. Select the confidence interval for P1 minus P2 to be at 0.95. And we get exactly the same thing. Lower limit 0.065, upper limit 0.455.